Dear friends, welcome to this electrical engineering knowledge sharing channel. Today we are going to start a new workshop 9. Under this workshop, we will be discussing about UPS system. This workshop might be containing various sessions or various videos which will cover the UPS system's basics, then UPS system, how to design UPS system, then to meet the industrial requirement, what are the various configuration we can use to meet or cater the preferred quality and uninterrupted power to the various industries. Then we'll go into the sizing calculation of the UPS system, battery system. Then we'll try to highlight about the manufacturing design or internal component details and design of the UPS system, including in UPS working principle or working line. So today we'll be discussing about the basic, and today's session, that is session 1 under workshop 9 or video number 75, we'll be discussing about the basics of UPS system and its system technology. For a single UPS, what are the technology we can use? That also we will try to highlight under this session. Let's start the system. Now this today's discussion is called, will be titling as a session 1 or it will be video number 75. Now when we look into the UPS system, today we are now, or most of the application is a solid state, using solid state technology UPS system. But if you go to the 1950 onward, up to 2000, you will see when the solid state devices has not come into the market or has not come into the system. At that time, all the industry, they use a dynamic or rotary UPS system. That is an old system. But with the development of solid state devices like diodes, thyristors, transistors, FET, MOSFET, all these once coming into the markets, then this rotary or dynamic UPS system has been replaced by solid state UPS, which is designed or made using these solid state components. So today's market, we are mainly use the solid state UPS system, even though some of the old installation or when there is a medium voltage or outdoor installation requirement is there, we can see that there is a rotary or dynamic UPS system is still existing. However, our discussion will be limiting within the solid state UPS system design and sizing and all other issues. But as we are now going to discuss UPS system, I am trying to give a small highlights about the old system. So when you look into the UPS system, we can divide the UPS system in two ways. One is a UPS system that you can be old system, that is a rotary system, rotary or dynamic UPS system, rotary or dynamic UPS system. And the today's design, what will be our main discussion will be the static UPS system, static UPS system, UPS system. So these will be, we will be concentrating our major discussion on this, but I just want to give a small highlight so that we'll be knowing how in the old days, how the uninterrupted power supply, this UPS means uninterrupted power supply. So when it's a UPS system, means uninterrupted power supply system. So in the old days, the rotary or dynamic UPS, how does it work? It is actually also sometimes called motor generator sets. So what has happened in this case, there is a power supply given to a motor. That motor, when it is rotating through a speed control device, we call it class. With the class, when it is control the speed, then it is going to a synchronous generator, which is producing the electric power, which is going to the load. That is if you see the rotary UPS system, there is a motor, and this is the induction motor, or if it is a 3-phase supply, it is induction motor. This motor supply through a class system, that is the speed controller class. class system, it is going to a synchronous generator which is producing power and going to the load. While this class system is mounted on the common shaft between the motor and the generator, and over the class there is another device is connected which is rotating with the same, which is called flywheel. This flywheel is storing the mechanical energy in the kinetic form, storing mechanical energy in the kinetic form. So this is a motor which is supplying by the power supply. Motor is rotating. It has a common shaft between the motor and the generator has a common shaft. Over the shaft, this class and the storing flywheel are mounted. This is called flywheel, which is mounted. So normal condition, motor is running through the external power supply, and through the class the speed is getting controlled and it is giving to the generator is a rotation. The generator rotor is rotating and the generator is producing power. And when the shaft is rotating, over the shaft also another mechanical device is connected which is called flywheel. The flywheel is rotating also with the same speed and it is storing the mechanical energy and keeping in this. So when this normal power supply fail, then the motor gets stopped, then the flywheel, whatever the energy is stored in the flywheel, that stored energy is released to rotate the rotor of the generator and the generator is producing power. This way, this rotary or dynamic UPS system used to work in the old days when the motor generator sets, we say, so that system work in this way. But as these all are mechanical device, maintenance of the mechanical device and cost, all this thing was very high, and with the development of the solid state various devices which I said already, like diodes, thyristors, transistors, FET, MOSFET, all these electronic devices, once it is developed and in the market, then with these solid state devices, new static system has come into the picture and which is flooded the market today. And most of the UPS system in the industry, we are using that UPS system which is designed based on the solid state components like a diode, transistor, all these things. That system we call a static UPS system, which we will be discussing today. Now, this solid state UPS system, if you look into the solid state UPS system, it has a couple of modules. These modules, if we look into this, solid state UPS or solid state uninterrupted power supply system has mainly the four system. It is the same logic. Here is a storing device is flywheel. In the solid state system, there is also a storing device. Here you have a input power, there is also input power, and that input power is converting to a running a generator to produce another power. Here is also the same way. We are giving input power, that power is converting and it is giving another output power through the intermediate device. And here, as in the rotary system, as there is a storing device, in the solid state or static UPS system, there is also a storing device. So if we look into the static UPS system, if we say a static UPS system, this static UPS system, if we look into this, it has mainly four modules. It has a four modules. One module we call is rectifier or converter, or you can say converter. Okay, second device or second module, it has a four modules. Okay, four modules. One module is rectifier or converter. Second module is a inverter. This is also another converter. It is a inverter. Third module is a battery. And fourth module is a static switch. These are the four modules which is making the UPS system, single UPS system. How and what is the function of this? The rectifier unit, it is actually how it is working. We show the rectifier in this way. This is if I show the block diagram, this is we show the rectifier. That means there is a AC supply. If I draw in a single phase way, we are supplying AC phase, single phase AC, suppose 240 volt AC, we are supplying to this device. This is a symbol of rectifier, which is converting AC supply to the DC supply. So the rectifier what it is doing? Rectifier is converting input AC supply to the output DC supply. How the rectifier has been made? that we will discuss at the end of this workshop. In the last session of this workshop, we will be capturing how this rectifier is made, what are the various components inside the rectifier, what is the working principle of the rectifier, that we will capture at the end of this workshop. Now, our main intention of this workshop to system design. That means I have the rectifier in hand, inverter in hand, battery in hand, a static switch in hand. How I will design the system, that is we are discussing. Based on that system, how we can configure the system to make sure uninterrupted power supply to the various industrial application as well as domestic application. Then we'll try to address the sizing and all these things what I have said. So these will be captured in the last of this workshop. So this, when AC supply is given to the rectifier output is a DC supply. DC supply, that means here I am giving a sinusoidal waveform. At the output of this rectifier, I am getting a constant DC supply. Suppose this is a 48 volt DC, I am getting like this, or it is 120 volt DC. I am getting this DC supply at the end of the rectifier. So this is a device which we call rectifier or converter, that is converting AC power to the DC power. So this is the rectifier device. Then the second device is the inverter. It is doing just opposite to the rectifier. In the case of inverter, what inverter is doing, here I am giving the DC supply. I am getting the AC supply. So here I have a constant DC. That means if we draw the voltage profile, here the input is constant DC supply. I am giving a constant DC supply. This is, and at the output, what I am getting a AC supply. Here I am getting giving positive and negative. Here I am getting phase and neutral. So here is how is the waveform? Waveform is, I am getting a sinusoidal wave, or it could be a square wave like this. Different way that we'll discuss when we will be discussing about the internal arrangement, internal components, working principle, and all these things we are discussing at the end of this workshop. In this workshop 9, at that time we'll capture all these things. At this moment, we'll just keep in mind that inverter is a device which is converting DC power to the AC power. The DC power could be positive and negative of various values. This output, it could be single phase or three phase based on the design of this. Okay, the input is always DC, but the inverter output, it could be single phase or it could be three phase, depending how these various components inside the inverter are arranged. Okay, so this is another device. Then the third device is a storing device. What is that storing device? That is the battery. We are very much aware, we are from the childhood, we are seeing the battery. So this battery, when you give suppose this is the symbol, how we symbol the battery? We symbol the battery this way, right? This is when this battery is giving extra power supply, DC supply from, it is positive and this is negative. This is, suppose this is a DC generator. If this DC generator run, then the positive supply will come, it will charge the battery, it will come back, and the battery is getting charged. So this is the battery, this is the third module of the UPS system. And fourth module is a static switch. This is actually a switch, two-pole switch. This switch is made of thyristors. So you know thyristors is a solid state device. We symbol thyristor in this way. So this is a gate. The difference between this thyristor and if we see the diode is like this. There is only one extra gate extra hand is here. That is we call gate. Difference between the diode and thyristor. In case of thyristor, to conduct the thyristor, you give a positive bias over here, a negative here, positive here, negative here. The moment it positive, in case of diode, what will happen? The moment positive anode is positive, immediately it will conduct. But in case of thyristor, it will not conduct based on the positive only. At the same time, you have to trigger the gate. If gate is triggered, and at that time, if the anode is positive, then only it will conduct. That means diode is a non-control device, but thyristor is a control device. I can control the thyristor conducting period by activating the anode, activating the gate. So that is the difference between the diode and thyristors. And this static switch is made out of thyristors using two thyristors. So there are two thyristors like this, and it is connected over here. This is a gate, this is a gate, this is connected over here, and then it is a using this thyristor device. Two thyristor device, actually it is connected back to back. You can say this is one is connected to one circuit and then the other one. Depending on the gate signal, it will conduct. This thyristor is connected to, this is a part of the static switch. So this is the fourth device of the solid state UPS system. Now if we look into this, how all are interconnected, but all the four modules are interconnected to offer us a static UPS system. So if we want to draw that diagram, how these four modules in the static UPS systems are connected, we can draw the system. First, we are giving a power supply. So this is the input power supply we are providing to the UPS system. Suppose then the first block of this is this AC supply to be converted to DC supply. So I have a first block over here, that is a DC, that is the AC input. This is the input, output is DC. Then the DC, what we are doing, this DC is getting charged to a battery. It is charging the battery. This is the battery here. Okay, this is the battery. This part is a battery. That is a module 3. I can say this is my module 1. As per this picture, module 1. This is a module 3. Charging the battery. And at the same time, what is happening? This DC is going to a inverter. This is my inverter. What is this doing? This DC which is coming from this rectifier, that DC is coming over here. It is converting to AC and it is going to the load. It is going to the load. That is my module number, module 2. Then the fourth module, what it is doing? It is connecting in this UPS. This is actually my UPS. But when the UPS system implemented, we have another arrangement. From this input supply, we take and there is we put a static switch over here. There is one thyristor over here. Okay. And then there is another thyristor over here. This is another thyristor which is connected. I am drawing in a single line. Okay. Then we draw over a single line over here. Then it will be more clear to understand. This is a AC supply input. Then this is connected to this point. So what is happening? This is one block. This is called a static switch block. After the static switch, it is going to the load. Okay. So this is the module number 4. Module 4. So if we want to explain how it is, this is the main supply coming from outside. Main supply. Okay. Main supply. Now this is a complete one UPS system. We can say this is a complete. When you say the UPS, this is called one UPS system. Simple, one single UPS system. This is a single UPS system. So in this case, you see all the four modules are there. How it is working in the normal condition, when this supply is available, external power supply is available, how it is working? It is working through coming to the rectifier. The rectifier, this part is energized. Rectifier, it is coming from the rectifier, battery is getting charged, and then this rectifier output is also going to inverter, and inverter, this thyristor is switched on. This thyristor is switched on. So what is happening? When it is switched on, the conducting path is like this. This is the conducting path. This is on. So power is going over here. At that time, this thyristor is off. Okay, this is a off. So no power is flowing. This is also connected. So the power is also coming. This normal main supply power is also coming this way. But if it is off, then it will not come over here. So only one path will be conducting. Okay. So this way, this in the UPS part is working. Now for any reason, suppose the main supply fail. It may happen. Suppose no main supply. Suppose now at any moment, if it happened that UPS system itself failed. UPS system itself fell. then what will happen? What are the alternative I have? I have the alternative, two alternative. If this total UPS system fails, then this inverter is not working. In that case, I cannot take the power from the battery. So at that time, main supply will come, and when this power supply fails, immediately the thyristor will give a signal. This failure signal will go to the solid state device, this static switch. Then immediately this gate will be on. That logic will be inside the UPS system. The moment this UPS output fail, this UPS inverter output drop, immediately this static switch, this thyristor will get on, and the bypass from this main supply which is taken tapping off, it will supply the load. Okay, that is one of the another operation. Now it may happen that instead of thyristor failure, main supply fail. When it is running from this UPS system, suddenly main supply fail. If the main supply fail, then what is happening? This is not available, and this rectification not possible because this is off. When the main supply fail, then what is happening at that time? If inverter is healthy, then the battery, which is a DC power, that will drain, that will discharge through the inverter, and inverter will maintain the power supply. Okay, so what about the conversion taking place? It will converting only normal condition in case of main supply fail or the rectifier fail. Main supply fail and the rectifier fail, in that case battery will drain through this. But in case of total UPS failure or inverter failure, in that case main supply will pass through the static switch. So this will be the following path. So these are the two different ways it can work. So this is the normal single UPS work on this. Here only difference, when it's changing from this supply to this supply, the static switch needs some operation time. It is about one cycle, means 20 milliseconds. During that 20 milliseconds, there is an interruption in the load. If the load is very, very sensitive, if it cannot withstand that 20 millisecond time, then we have to think for the other arrangement that will come afterwards. So this is the basic solid state UPS system. Now this basic solid state UPS system, these things we said, this is called our bypass line. This is called bypass line, bypass supply or main supply. In that case, what is happening? This UPS supply is very regulated, and the waveform, all this thing we can control. You know, when the rectifier is done, in the output voltage, it is not perfect DC. There is a ripples, harmonics, all this thing is there. So use a various filters. Then also this, when the DC is converted to AC, there is also various ripples will be there, harmonics will be there. All this thing is getting filtered, and then very smooth wave, very smooth the UPS is a sinusoidal waveform, very smooth sinusoidal waveform UPS output will be there. But when we are using the main supply direct this way, without all the filter everything, this bypass supply, it has a lot of harmonics, because this harmonic coming from the main line, which is not under our control. Here in the UPS design, we can control the harmonics, we can control all the ripples, so that harmonics are controlled. We can regulate the waveform. All this thing we can do in the UPS system design, the rectifier and inverter design. But when I am taking the outside main supply direct to the load, I don't have all this control. So in that case, the bypass supply is not the regulated supply. So lot of ripples, harmonics, all this thing will be there. If the load is very sensitive to this, then we have to think alternatively how we can do that. So alternative thinking is coming due to two reasons. One reason is due to this thyristor switching time, and due to the various ripples in the system. So these are the basic structure of the solid UPS system. So solid UPS system, we understand there is a UPS, complete UPS, and then there is a bypass line which is connected to the load through the static switch. So this is the basic of the UPS system. But now to avoid this harmonics issue, and you know the main supply which is going from the bypass line. So if this is my UPS system, this complete UPS system, if this is my UPS system, I am giving main supply over here, and then I have a static switch over here. Okay, so a static switch, I can say this way, this is a static one path, this is the bypass, and this is the main supply. Main supply is coming from here, And what I am doing, I am giving the bypass supply from here, and then it is going to the load. Suppose this is going to the load. So bypass supply is coming over here and it is going to the load. So when the or it is coming over here, not here, it is coming on the static switch over here. Here. So bypass supply is going this way, and when the static switch transferred to over here, it is going this way. And normal condition, main supply through the UPS and through the at that time static switch over here. So it is connected over here, it is going from here to here to the load. So this supply has no control, we don't have the control on this supply, but this UPS output we can control by designing the or incorporating all the necessary devices inside the UPS system. So we can get a constant output voltage as well as sinusoidal waveform with a ripple or higher frequency harmonics to the desired level. But in the case of bypass supply, the main supply voltage, if there is a voltage, main supply is not supplying always constant voltage. If it is 240 volt, we will not always get 240 volt. 240 volt will be fluctuating, but that fluctuating voltage will be going there, as well as in incoming supply, whatever the ripples, harmonics, all this thing will be going to the load. If the load is sensitive to that, in that case, running in this way is a not very appropriate. So we have to find the alternative. Okay. So this is the basic structure of the UPS system. Now, depending on this UPS system technology, we have classified the UPS system, solid state UPS system, single solid state UPS system under 3 categories, depending how the system is working. You have seen you have 2 supply. One is a supply going through the UPS, another is the bypass supply. These 2 supply, how it is working, which is the one, which is off. Based on that UPS system, single UPS system, we can divide into 3 parts. What I said, this is my UPS system, this is my bypass line. Through the static switch, it is connected to the load, right? Through the static switch, it is connected to the load. Now my condition is whether this part is working or this part is normally working. Which is normally working? Based on that, the UPS system, single UPS system, we can divide into 3 different categories. What are the different categories or different class? One is called offline UPS. Offline, from the name you can make offline UPS. Offline UPS system. That is one classification. Second classification, we can say this offline online UPS system. Online UPS system. And third one, it is also offline. It is a similar to offline, but it is interactive. Interactive UPS system. Offline interactive UPS system. These are the 3 different type of UPS system we can design based on the load requirement. Okay. So let us discuss one by one. From the name itself, you can make out the offline UPS system. If we look into the offline UPS system, how does it work? So if we draw the UPS system, how it is, I have already shown. This is our rectifier. Then the rectifier is connected to the battery. This is negative, this is positive, negative, this is positive, this is negative. This is our battery. Then third module is your inverter. That is your DC to converting AC. And then I have a static switch over here. There is another static switch over here. This is a static switch module and it is going to the load, right? And then the bypass is connected over here. This is the way, this is the bypass line. And this is the inverter line. It is inverter. So this part we call is a inverter, right? This part we call inverter. This is by inverter. In short, we say inverter, but this is our complete inverter system. Okay. Inverter system, it is a rectifier, battery, then inverter, and the static switch also. This part also you can consider under this. And the bypass, what is the bypass? Bypass is this line and this static switch going to the load. Now, which one is normally on? Offline UPS means, what does it mean? This UPS is not working. In normal condition, UPS is off. This inverter is not working. It is in normal condition, what is it? It is off. In case of offline UPS system structure, in the offline UPS system structure, UPS, this inverter part is off. Inverter is not working. So what is happening? Normal condition, the bypass supply is going through the thyristor to the load. Normal condition. And at this, it is a normal operation I am talking. In the case of offline UPS, if we say it is offline UPS, in that case, in the case of offline UPS, bypass supply through the thyristor, through the static switch going to the load, and at the same time, the supply, it is taken from the same main supply. This is external main supply. The main same supply is connected to the rectifier, and rectifier is charging the battery. That means this part and this part is live. This part is totally live. In the case of offline UPS, this part is live and this part is off. This part is working, means main supply giving to the load as well as main supply through the rectifier, it is charging the battery. In the case of offline UPS, this is the normal operation. Now, main supply in most of the time, in 90% or 95% time, main supply is always available. In that case, main supply will go to the normal. Only problem, this main supply has no control. Means this voltage, if there is a main supply, there is a voltage fluctuation, same voltage fluctuation will go to the load. If the main supply has harmonics, then also all the harmonics will go to the load. If the load can sustain this thing, in that case, the bypass supply in the offline mode configuration, it will running through the bypass supply. The moment main supply fail, what will happen? In case of main supply fail, at that moment, what is happening? Then this rectifier is not working, right? Bypass is off, main supply is off. Main supply is off means bypass is off, rectifier is not working. At that time, this battery is discharging through the inverter and it is catering to the load, which is a good quality of power. So in the case of offline UPS, normal condition, UPS is off, inverter is off, rectifier and bypass is on. But the moment this normal supply, main supply fail, immediately this battery and inverter will come into picture and it will supply. Okay. And third is, if the total UPS system, either rectifier or bypass inverter, all either rectifier or inverter both fail, or any one of them fail. Okay, if the inverter fail and the UPS system, total UPS system fail, in that case also main power supply will go. But both, if the UPS fail and main supply fail, then we cannot do anything, because we do not consider two systems fail at the same time. At one time, when you discuss the failure mode analysis, we always consider one failure. That means either the UPS failure or the bypass failure. So as the normal condition, the loads are running from the bypass and UPS is offline. UPS means inverter part is offline. That's why we call it a offline UPS system. In most of the domestic application in the house, you say most of the houses in the rural areas or in the suburban areas, most of the houses, they have an inverter, battery feed inverter. How that is what they work in this way. Normal condition, this bypass supply is, or the main supply going direct to the load as usual. The moment main supply fail, this main supply fail, immediately what is happening during the normal operation, when this battery is getting charged, this battery is getting discharged through the inverter and that is supplying power to the load. Because most of the domestic applications now in the house, domestic house, they can withstand the main supply fluctuation. So in that case, bypass supply is continuously supplying most of the time, 95 to 98, 99% time, and the balance 5 to 1% time, only UPS will be running. So this is called offline UPS system. Advantage of this is that in that case, inverter is not always connected. So inverter operation time will be very less and the battery is not subjecting to discharge continuously, so the UPS system life will be very high. If it is a 10 years, it may go 15 years. And second point, these UPS system, as all are solid state devices, there is a lot of power consumption inside which is emitting from the system as a heat. That is the loss of energy. So system efficiency will be electric bill, the main supply when it's coming running through the UPS system, although the output voltage profile, frequency, all this thing will be good, but the loss inside the UPS system will be catered by the main supply. That will increase the electric bill of the consumer. So in case of offline UPS, advantage is UPS cost, this equipment rating, we can reduce the rating or sizing, and it will reduce the capital cost, and it will also reduce your total electric bill, because most of the time it is running by this way, only the electric bill will be more in case it is running, but it is running only 1 to 5% time, 95% running time through this. So if I design this type of UPS system to a load which is not very sensitive to the voltage fluctuation or the harmonics, which is mainly in the domestic application, we can use the offline UPS system. Okay, so that is the offline UPS system. Now if we go to the online UPS system, how does it work? It is the same logic. We can erase from here. In case of offline UPS system, it is the same arrangement as we draw. This is my rectifier, then this is my battery, and then it is going to the inverter, right? This is my inverter, and then I have a bypass, and through the static switch, this is a static switch over here, it is going to the load, right? So in case of offline UPS system, you can make out from the name itself. Online UPS system is, UPS system is normally online. That means in normal operation, under normal operation, what is happening? These both are live. This is a on, this is a on, and this is a on, and power is going through this. And this is off. This thyristor is off, means bypass is not going from this. And the battery is, this rectifier, when the rectifier is on, it is doing two jobs. One job, it is supplying power to this, at the same time it is charging the battery. Okay, so this is the way. In case of online UPS, that means 95% time it will be running through the UPS system. So the loads will continuously, most of the time, 95 to 99% time, load will be getting very good voltage profile, smooth voltage, low harmonics, which is controlled through the system. The moment this inverter fail, which is considered as a UPS failure, the moment UPS failure, then what will happen? There is under voltage over here. Immediately, inverter will give signal to this thyristor to on. So because when the under voltage is there, immediately this thyristor reverse bias, it will not flow. Immediately this will give a signal, the control card, there is a control card inside that will give a signal to this thyristor, and this thyristor will be on and power will be going through this and it will go to the load. So this only 1 to 5% time this may happen, and load will be subjecting to the voltage, this main supply, which may be very clean supply or is maybe some dirty supply, means it has some voltage fluctuation and harmonics, but only 1 to 5% time that will happen. If it is works in this way, we call it online, because most of the time UPS is online. And in case of main supply fail, as the moment main supply fail, then what will happen? Then battery will discharge through the UPS system, it will run through the UPS system. So most of the time you can say it will run through the UPS system, and as the UPS system online in normal condition, we are calling it as an online UPS system. Okay, but this 5% time only when this inverter fail, 5% time when the inverter fail, at that time what is happening? This bypass will go through the static switch to the load. This bypass supply, it may be clean supply or may not be clean supply. This is the online UPS. Now, if we put an interactive UPS system, that is similar to offline UPS system, but this interactive UPS system is designed, why? To considering the load requirement. If the load is very much sensitive to voltage fluctuation, harmonics, all this thing, in that case, we can use this offline interactive UPS system. Here, normal UPS system is working in the same way as before. There is no change. Normal supply is coming here. This is my UPS system. Okay. This is a AC. This is a DC output. It is going to battery. This is going to battery. Okay. And then it is going to my inverter. This is my DC and this is my AC. It is going to through the static switch. It is going to the load. Right. This is the normal. In the case of this is when the UPS, it is a main supply, outside main supply. When the main supply is available and if it is running UPS, it will low in that way. But we call it offline interactive system. Why it is called like this? Now the bypass line, which before we take directly from here, right? In the case of, in the previous, either online or offline, in both cases, we take directly through this, right? Now, in case of offline interactive UPS system, this bypass supply, if the load is sensitive to voltage fluctuation, to avoid that fluctuation, when this load is running from this, as it is offline, so most of the time it will be running from this, right? In the case of, as it is interactive UPS system is offline UPS system, so 95% time, 95 to 99% time, it will be running through the bypass. But if the load is sensitive to voltage fluctuation or the harmonics, then we can modify the bypass line. How? There are two ways. One way is we can incorporate one device over here which can smooth the voltage, means which can control the input voltage variation. Suppose the main supply, which is raw supply or dirty supply, if that supply we can control the output voltage, then the output voltage we can supply to the load, same like UPS. So to do that thing, to control, to minimize that input voltage variation to the output, we incorporate one device over here. That device is smoothing this input supply and giving to the load. This is the additional device we are incorporating inside the offline UPS. When we are incorporating this external device, additional device in the offline UPS, we call it offline interactive UPS system. This device, there are two types of device available in the market. Now, what are these two devices? The number one device is a buck boost transformer. We call it a buck boost transformer. This is a one device transformer. Okay. Second device is called ferro resonance transformer. Ferro resonance transformer. These are two devices. Any of the device we can use it, but it has a different cost and different working principle. Buck boost transformer, that means it is offline. It is offline UPS, but in this offline UPS, when the bypass line is incorporating any of these devices, then this offline UPS is called offline interactive UPS system. So first let us consider the buck boost transformer. How is it? Now the buck boost transformer is actually multi-tap transformer. How it works? There is a primary winding. This is a primary winding. On the secondary winding, we have a multiple taps. Okay, and there is a tap changer switch. This tap changer switch is operating by a motor. You can say this tap changer switch is not operating manually. There is a small actuators over here which is getting power supply. Okay. Now this tap changer, suppose this tap changer switch, this switch is going out. Now this tap motor, how the motor is getting activated? Now this is the input voltage where I don't have control. Suppose it is 240 volt input, this supply. This back boost transformer is this one. This is a transformer. The input side is this. This is the transformer, okay? This is a back boost transformer. The input supply 240 volt is coming over here. Then output is not fixed. Now what is happening? There is a output, there is a relay connected. Between these two, there is a relay connected. This relay sensing the output voltage. The moment it senses, suppose the output voltage fixed at 240 volt, fixed value. Okay. So the moment this voltage goes up or goes down, immediately this relay is activating. Okay. Relay is activating in the moment for the, suppose there are two relay. One relay is activating on the up voltage. Suppose this voltage get 242, immediately there is a relay R1 is activating, and if this voltage come down to 238, then another relay R2 is working. There are two relays, you can say in that way, which is activating by this output voltage. So the moment this output voltage is goes up or goes down, immediately respective relay is working, and this relay is giving signal to the motor either rotate in the forward direction or reverse direction. And the moment it is a, suppose it is the rotating forward direction means this way. So suppose this, so it is going to here. That means normal condition it is here. So it is going over here. So then it will get one voltage. But if it goes over here, it will get better voltage. So depending on the requirement, on the relay activity, this actuator is rotating either this direction or this direction to select the tap, and accordingly output voltage will be maintaining constant. So it is like your on-load tap changer. You have seen that on-load tap changer in the transformer. It works in the same way. So if this transformer is added over here, it is called buck boost transformer. Buck boost transformer. If I use the buck boost transformer in the bypass line to get the better voltage profile on the load, then we call is a offline interactive UPS system. So this is one of the way we can do this. But here you have to keep in mind, these will not reduce the harmonics which is in the main line, because it is only changing the voltage but not the harmonics. That means quality of the power is getting corrected from one sense, that is the voltage point of view. But if we want to clear or purify the input voltage from the harmonics point of view, it will not work out. Rather, it may include more harmonics, because this tap changing, there may be arcing during the tap changing by the actuator. There may be arcing, and the arcing is a high frequency. There is a lot of high frequencies generated by the arcing, or during the tap make break on off, make break also creating lot of harmonics. That may cause in the load will be more dirty. So, but voltage value will be good. So if the load is such that it can accept the harmonics but cannot accept the voltage variation, then we can use a buck boost transformer in this place. Okay. But disadvantage of this, what is that? When you add a additional device, because 95% time this device will be live, this device will be activated, it will remain live. Transformer has additional loss. The loss will be coming into the picture. That will increase the power requirement. So automatically it will increase the bill. Electric or consumer bill will increase, and it will produce a more heat, because whatever the power loss taking place in the transformer, the loss will be radiated as a heat. So the cooling, it needs cooling will be required. There will be fan. It is so those fan running cost also will be coming into the picture. So it will be more expensive. In other way, it will be more expensive, and from the efficiency point of view, efficiency of the overall UPS system will be also lower, because 95% time it is running through the buck boost transformer. So all the losses will be coming into the picture. So automatically output power and input power, the amount of input power you are giving, output power you are getting less, because there is a loss inside this. So efficiency of the system will be also less. Okay. And cost will be high, because this additional device you are incorporating. Maintenance cost also increase, because there is a rotational device. This tap changer, switch, actuators, if any one of these fail, you have to replace it. So maintenance cost or operational cost also high. Capital investment also high, because this additional device included, but it will provide a better profile voltage. Okay, this is a buck boost transformer. Then the same device, same arrangement, it is offline arrangement, but instead of buck boost transformer, if I use a ferroresonance transformer, then it is also a called interactive UPS system, but this device will be ferroresonance transformer. Okay, what is this ferroresonance transformer? That is, you have learned, you may be knowing this thing. Actually, normal transformer, normal power transformer, which we use in the power system, you know the transformer, how does it work? Transformer works, or the transformer develops the voltage. We give the input voltage, and then there are two windings. On the primary winding, we give the input voltage. On the secondary winding, we get the output voltage. How we get it? So this is the primary winding and this is the secondary winding. These two windings are connected with a magnetic flux. How the magnetic flux is growing? This is a magnetic core. Then this winding is wrapped on the core. Okay, the moment we give the power supply, the core is magnetized. It produces a flux. That flux link at the secondary core also, secondary winding also winding on that core. Then this flux is linked with the secondary, and if that flux getting changed, then it will produce a voltage. We know the voltage equation. Voltage on the transformer winding, if we look into this, that is equal to N, if there is number of turn, N into d phi dt. d phi dt. N is the number of turns in the secondary, any winding. When you check the voltage of the input winding, V equal to N into d phi dt. If we take the secondary winding, N into d phi dt. In that case, the amount of flux linked with the secondary winding, rate of change. Now, in case of sinusoidal wave, what is happening? This is the sinusoidal wave. So, continuously flux is changing. So, there is a continuous voltage is developing. So, in case of voltage in the secondary, N into d phi dt. Now, as that means voltage developed on the secondary is proportional to the d phi dt. N is a fixed. For the winding, N is fixed. The more the d phi dt, if the d phi dt as is higher and higher, voltage will be higher and higher. If the d phi dt is very less, automatically voltage will be less. Suppose it is producing a certain voltage change. Now, if the voltage sense suddenly goes up, voltage sense, that means input voltage when they going up, then automatically this will be also, the flux will be also different. So, voltage develop in the secondary winding depending on the rate of flux. So, now this rate of flux in the case of normal transformer, how we design, if we see the magnetic flux curve or magnetic saturation curve of the core, how does it? That is, we know from the hysteresis diagram. If now we are considering 0 means 0, I am not talking hysteresis loss. It will be like this, right? So this is a linear portion, and this is going to saturation portion. Okay, this is going to saturation portion. I am doing like this. This side is a voltage, input voltage. This side is a flux phi. Okay. Now, in the case of normal transformer, how it is a magnetic flux curve of the core. Any iron material, we can draw the magnetic flux curve. This is the input voltage to the core, and this is the flux produced by the core. Now, normal transformer always designed in this area, in the linear area. So, this change of is constant, change is a linear change. So, if I design the transformer at this point, so with respect to this point, the sinusoidal, this is the RMS value. So, with respect to this point, as it is going up, variation is high. Suppose you see, you change the voltage this amount. How much flux change is there? Flux change is this amount. This is the flux change. For this amount of voltage change, it is more or less constant. Same amount of voltage, same amount of flux. So, normal transformer working in this case, so I need a small core. In this core will be a smaller because the flux, we need this amount of flux density, so core will be a smaller. But here, and this flux, on what basis the flux is depend how much current going through the core, that depend on the voltage. As the voltage increases, current increases, automatically flux increases. That means current and flux is directly proportional. As you increase more and more current, more and more flux will be produced. Okay, because to increase the current, you have to increase the voltage. Okay. Now, if the transformer is designed at this point, suppose the transformer is designed over here, then what will happen? Now you see here, you take 2 points over here. Suppose this is one voltage V1 and this is one voltage V2. Transformer is designed at this point. Now, if we change voltage beyond to V2, how much flux change is taking place over here? Very less, right? These amount of input voltage variation, but ultimately this change of flux is very less, very less. So if I use a transformer whose core is designed at this near to the saturation point of the magnetization curve, then what advantage I will get? Input voltage variation will be very wide, but the output voltage variation will be very less because this flux change is not there. If the flux change is very less, automatically voltage in the secondary V2 n into d phi dt, right? But d phi dt is very less, only this amount. But in the previous case, d phi dt is this amount. So in that case, my V2 voltage variation will be very less. At this point, whatever for this voltage, whatever the V2, and for this input voltage, V2 will be more or less same. So I will get this advantage. If this UPS system bypass line, we use the magnetic core of the transformer and design the core at the saturation point of the magnetic curve, then what will happen? In that case, this transformer will be working on this ferroresonance principle, and then the output voltage of the transformer will maintain more or less constant. So what will happen in that case? Harmonics, in that case, voltage fluctuation of the input will not reflected to the load. That is one point. Second point, this ferroresonance transformer as is working in the magnetic saturation region, you know, in the previous, in all cases, when this changeover take place between these two switches, static switch, there is an interruption about 20 milliseconds, right? About 10 to 20 millisecond interruption time is there where the load will not get power. But in this case, in the case of ferroresonance transformer, what is happening? It will take the voltage fluctuation, it will take care of the voltage fluctuation and give the output voltage constant. That is one point. Second point, as the magnetic core is always saturated, so the moment power supply fail, is still there will be output voltage, because this flux density will not come suddenly zero, it will take some time. So during that time is the transfer time. But by that time, this ferroresonance transformer, though the main supply is not available, but the ferroresonance transformer, due to the storing magnetic energy, it will release that magnetic energy as a electrical energy through the static switch to the load. So interruption will not be there. And as you know, the transformer is a DVDT device. It is a differential device. So transformer itself acts as a filter. Choke unit, you know, transformer itself is inductor. So it is also, and it has a capacitor. So it is a very good LC filter. So whether we are using buck boost transformer or we are using ferroresonance transformer, we can reduce the harmonics to some extent due to the differential property of this. So due to this buck boost transformer, whatever the amount of frequency harmonics we can reduce, in the case of ferroresonance transformer, that can be reduced more. So ferroresonance transformer will provide a constant output voltage as well as a more or less pure electrical energy to the load. And buck boost transformer also will give a good profile voltage, but harmonics will not be so good as like this, but it will also reduce the harmonics with respect to the normal offline UPS system. So when the load required a good profile voltage and good quality of supply, in that case offline interactive UPS system is a better preferred, though it has a high cost and the low efficient, because the additional device has a lot of heat. This ferroresonance transformer will produce a lot of heat. That heat also to be eliminated from the UPS system through the fan, and that is a loss of energy. So from the electric bill it will not be preferred, but if the load is like that, it needs constant voltage and the pure high quality power. In that case, we have to use this either buck boost transformer or ferroresonance transformer in the case of UPS solid state UPS system design. So with this is all about single UPS system and its various type. So we discuss normal, in the old days we use the rotary UPS, we have discussed in very brief. Then we have discussed about the solid state UPS system, how it is configured, how is the combination is there, and how the solid state UPS system, what are the different type we can use it. That also we have discussed 3 different type: offline, online, and offline through offline interactive UPS system. And more or less we have discussed about the different various merits and demerits. With this, I am closing this today's session 1 of this workshop 9. Next session, we will use a UPS system configuration to avoid this interruption time break to the load, as well as to get a good quality power to the bypass line. So that will be using this arrangement, but it will be multiple UPS system will be connecting to avoid this load break, that 10 to 20 millisecond time that we'll discuss under the UPS configuration to be used in the various application in the industry, that we'll discuss in the next session. So that's all about UPS system today's session. Please go through this. Please take note that this is not my profession. Out of my pleasure, I am making all this. So if somebody gets benefit, that is my pleasure. I am not making these videos, all this thing for YouTube money or anything. It is only my interest and my desire, and whatever the experience I have gathered over my working life, out of that knowledge, in the part of design, whatever I have gathered, that part I am trying to portray in the writing form to you all. And if somebody gets a benefit out of this, that will be my pleasure. Please go through this and share with your friends as usual. And if you have any observation, please, if you want to see any other comment, any other videos on this UPS system, please let me know. But I will try to cover all this basic requirement to design a UPS system for any industry. I am not going to discuss in details to the manufacturing design, but I will discuss how to design a UPS system for any industry as a engineering consultant or engineering operating team or site supervisor, site maintenance, how they will think for the UPS system to be designed. That I am trying to highlight over here. So keep it on. Thank you very much indeed. Thank you.